All right, page 311 was the assignment. So hopefully either you watched the other video that went along with this one that showed me working problems off of page 311, or the substitute. Worked through some of the problems on page 311 with you if you had questions. What we're going to cover today: indirect measurement. We probably mentioned indirect measurement a couple of classes ago. Indirect measurement is measuring something but not measuring it directly, so not actually using a tape measure, ruler, or something to measure whatever it is that you're dealing with. We're going to talk basically about three basic kinds of indirect measurement. One's the shadow method, and I call it shadow method 1 because there's actually two ways that you can use a shadow. Second one is a mirror method, and then the third way is shadow method 2. And I'm going to show you a slide for each one of these and draw some pictures to help you understand how to set up your proportions and match up the similar triangles. Now, the good thing about each one of these is you're going to understand, hopefully, that each one creates similar triangles, and I'll show you that. And after you show it once, if you're doing shadow method 1, then you should realize that, hey, if it worked once, if the triangles are similar, then it's going to work every time after that. All right, so shadow method 1. And I'll just draw a picture here. If I have a building, maybe I'm trying to find the height of that building. That building has a shadow, and I'm standing over here, and I have a shadow. Well, what's formed here is the sun's rays. The sun's up here. This thing wouldn't switch on me. The sun's up here, and it's shining down on the building, and it's shining down on me. Well, what's formed is two triangles. And not only are those two triangles, but these triangles are similar to each other. And we can show that they're similar to each other because, first of all, the building hopefully forms a right angle with the ground, and hopefully I form a right angle with the ground. So that's one pair of angles, and all we need is two pair of congruent angles to show that the two triangles are similar. Well, the sun shines down on the building, and as long as I'm within a reasonable distance from the building's not in New Paris and I'm in China, then the sun's shining on me the same as it's shining on the building. So this angle that the sun shines or forms with the building has to be the same as the angle that the sun forms with me. And then we know that these two triangles are similar because of our angle-angle theorem that we talked about a few days ago. So if we have that, then we know that these two triangles are similar to each other. And the way you could set up your proportion here is probably the easiest way is to go the height of the building, whatever this right here is, compares to my height, the height of the person. Don't get this confused in science class or anything else. With the shadow of the building comparing to the shadow of the person. So if I put some letters on here, maybe I call this A, we'll call this, let's not use B, we'll call this C, we'll call this D, we'll call this E, then our ratio would be A compares to D, the same as C compares to E. So building height compares to person's height, same as building's shadow compares to the person's shadow. So you can do it that way. There's actually other ways you could set it up. You could compare the building's height to the building's shadow, and then the person's height to the person's shadow if you wanted to set it up that way. I'm not going to write all that down just because if I show you one way, I think if you do them that way every time, then you won't get them mixed up and confused and mess up where each thing goes. The next one is the mirror method. And in this method, let's say we have a building again. And we have a person that's trying to measure the height of this building. Well, they're both standing on the ground. If we have that, and what this person can do, and if there's no shadows for them to look at, they can place a mirror on the ground in between them and the building, and then the person can move so that they can see the top of the building maybe right in the middle of the mirror. So the top of the building is going to be right there in the middle of the mirror. And then what we have formed from the top of the building to that point in the mirror, and from the person's eyes to that point, we now have two triangles. And those two triangles, even though mine doesn't look like it, those two triangles, hopefully this is a right angle again, so this angle is congruent to this angle. And the angle that the person is looking down into the mirror is going to be congruent to the angle of the reflection of the building coming down to the mirror. So these two triangles have to be similar to each other by angle again. Well, if that's the case, then the proportion we can set up is, again, we'll go the height of the building compared to, that's the height of the building over here, compared to the height of the person. Oops, let's make that a small p, doesn't matter real. Let's see where it's at. Height of the person, and then the distance the building is from the mirror. So building, or distance for the building from here to here, and the distance the person is from the mirror. So if I put some letters in there, we'll go X, Y, Z, W. Our proportion is just going to be X compares to W, the same as Y compares to Z. So you set up that proportion. And that would allow you to solve for whichever one you're missing. You're probably going to be missing the height of the building because that's the one that you can't normally measure. Normally you'll know the height of the person, and you can measure the distance the person is from the mirror. You can measure the distance the building is from the mirror. So the height of the building is the one that we would be indirectly measuring. The last one, shadow method 2. We have our building. It's got a shadow. Then we have our person, and what the person does is they stand on the building's shadow so that their shadow matches up perfectly at the end. And then what we have, and mine's not gonna come out real great, the person's head should be way up here, because otherwise the sun wouldn't be hitting them at all. So we have the person standing there, and we have this picture that looks like this that we dealt with in the past, where hopefully the building and the person are parallel to each other because they both form 90-degree angles with the ground. That means those two angles have to be congruent. And we also know that these two are congruent because they are corresponding angles with the parallel lines, and also that's the angle that the sun's hitting both the building and the person. And then what you have is you have two triangles there. You have the building's triangle, which is the bigger one, and you have the person's triangle. Sorry, that messed up. You have the person's triangle, which is the smaller one. And you know that this angle is congruent to this angle, is congruent to this angle. So that's enough to say the two triangles are similar because of angle. If that's the case, then the proportion we can set up is building's height. So height of the building compares to the height of the person, the same as the building's shadow compares to the shadow of the person. And that's sort of the same one as the first one, but what you got to be careful of again is this distance down here isn't going to be, you're going to maybe know that whole distance and maybe the person's distance, but you probably, or you might know the distance the person is from the building, and you might have to add or subtract to get one of the other distances. So maybe an example would be, maybe you know that the whole distance is 50 feet, and the person is 30 feet from the building. Well, if the person's 30 feet from the building and it's 50 feet the whole thing, then that means the person's shadow out here has to be 20 feet. And you use that in your proportion. And again, I'm going to do some letters over here on these bottom ones. Maybe we use Q, R, T, and V in our proportion. Then if we split up the two triangles, again, making sure, being careful when you find R and V, because you have that overlapping links in there. It's going to be Q compares to T. This compares to that. The building's height compares to the person's height, the same as R, the building's shadow, compares to the person's shadow. All right, on the worksheet, do a couple of these problems. If you're on the side, it's page 480. Do number 1 first. I'm only gonna do a couple of them. Hopefully this gives you the idea. You have your flag over here. You have your tree standing here. They tell you that this is 18 feet. This is 45 feet. And the tree is 10 feet tall. And they want to know how tall the flagpole is. So again, we know we have similar triangles because this angle should be congruent to this angle. And the angle that is coming down here, since the tree and the flagpole hopefully are parallel, this angle should be the same as this angle. And if we split off those two, we have the flagpole's the tree's triangle. This is for the tree. And we have the flagpole's triangle, which is the bigger one. Well, we know the tree's height is 10 feet. We don't know the flagpole's height, so that's our X. That's what we're looking for. Down here we know that the tree's shadow is 18 feet. This distance, this is where you got to be careful. That distance is the distance from here all the way to the flagpole, so it's that whole thing, which is 18 plus 45, which gives you 63 feet. Then you can set up your proportion. The height of the tree, which is 10, compares to X. You could have switched those around or whichever. The same as 18, that's the tree's shadow, compares to the flagpole's shadow, which is 63. We cross multiply, 18X, 10 times 63 is 630. To find X, you divide by 18. These cancel out, you're left with X. If you have a calculator, you could use it. 630 divided by 18. 3 times 18 is 54. Leaves us with 90. 5 times 18, 5 times 8 is 40. Carry the 4. It's 90. So X equals 35. That tells us that the flagpole is 35 feet tall. All right, we'll take one from the back of the worksheet. Let's see. Let's just do on page 481, that's the back side. Let's do number 18. It says a 25-foot ladder is leaning against the wall. So we got some ladder leaning up against the wall here. A rung that is 5 feet from the bottom of the ladder is 4 feet above the ground. So you got some rung that's 5 foot from the bottom of the ladder. So this distance here is 5 feet, and it's 4 feet off the ground. So that's that. We got the ground down here. How far above the ground does the top of the ladder reach? And the thing I forgot is they told us this whole ladder was 25 feet. Well, we've got two triangles here, and hopefully the building, and this makes a right angle, so those two have to be congruent. And the angle here and the angle of the ladder mixed with the building have to be congruent, so we know the two triangles are similar because of, pen's messing up, because of angle. So if we have our two triangles, we have the big triangle, we have the little triangle. We know that this side's 5, this side's 4, this is 25. We're trying to figure out how high up the ladder goes, which is this. So we're looking for this, we'll call that X. And we just set up our proportion. 5 compares to 25, and again, you could have turned them around and did it that way. Same as 4 compares to x. We cross multiply, you get 5x equals 100. Divide by 5, x equals 20. That means the ladder will go up the wall. Go up the wall 20